Analytes concentrations based on its absorptions of ultraviolets or visible radiations ang isa ka most frequently encountered sa quantitative analytical methods. Isa sa reason sa popularity ang kadaghan sa organic and inorganic compounds which have strong absorption bands in UV-Vis regions of electromagnetic spectrums. In addition, if ang analytes wala nag-observe of UV-Vis radiations, if its ang observance is too weak, we often can react it with another species that is strongly observing. For example, ang kaning dilute solution sa iron positive 2 charge wala nag-observe of visible lights reacting kaning iron positive 2 charge with of phenolphthalein. However, ang forms an orange-red complex of iron phenolphthalein that has strong broad observance band near sa 500 wavelengths. Here's the illustrations of observance and wavelengths. Sa makita ninyo, ingon dool sa 500 wavelengths ang high observance that they observe. This happens during sa charge transfer observations which is important kay nagproduce siya og very large observance. So in charge transfer observance which possible in electron moves from the ligand to the metal. In iron phenolphthalein, where is the ligand is of phenolphthalein, maybe you ask yourself why is larger observance is desirable because ang analytical methods is very sensitive. Very sensitive if a smaller concentrations of analytes gives larger signals. Ang sa wavelengths nag-correspond sa maximum observance. Para, that's it, ang wavelengths nag-correspond siya sa maximum observance para sa target substance gipili for analytes. This ensures ang maximum sensitivity, the larger signal is obtained para sa certain analytes concentrations. Now, in Burst's law, ang advantages sa UV-Vis absorptions is that in most cases it is relatively easy to adjust experimental and instrumental condition which the Burst's law must obey. In quantitative analysis based sa observations sa infrared radiations. Using infrared radiations, one reason is the greater tendency for instrumental deviations. Isa sa reason nga nung dako ang tendency sa instrumental deviation from Burst's law when using sa infrared radiation because ang infrared observations band is relatively narrow. Any deviation due to the lack of monochromatic radiation is more pronounced. Infrared sources are less intense than UV-Vis sources. The difference between sa pathlets for samples and for standards is mogamit og thin liquid films. Finally, establishing 100% transmittance observance equals zero baseline significantly with wavelength due to the contaminations and degradations, where ang is the transmittance often is difficult because the optical properties of sodium chloride sample cells may change. Here's how to accomplish. In the vertical area are the percents of transmittance, and here the horizontal area are the wave number. You can see in the 900 wave number is the PT were called the region power transmitted, and the P0 are the source region's power. And here's the formula of the observance equals to negative log PT over P0.
So the qualitative application of the UVVs, so under the molecular spectroscopy, so the ultraviolet, visible, and infrared absorptions bands result from the absorption of electromagnetic radiation by specific valence electrons or bonds. So UVV spectroscopy is an analytical tool that allows us to determine the purity of the analyte, and it does not undergo decomposition. So the qualitative analysis technique is used to used to perform quality control checks of the raw material and biological relevant compounds such as nucleic acid, the DNA, and RNA. So the energy at which the absorption occurs and the intensity of that absorption is determined by the chemical environment of the absorption, we would say. So for example, so benzene has a several ultraviolet absorptions band to bands to pi transition. So the position and intensity of two of these bands is 203.5 nanometer and 254 nanometer are sensitive to substitute. So to identify the functional groups or confirm the identity of the compound by matching the absorption spectrum. So to identify the unknown compound, wait. So to identify an unknown compound often can be determined by comparing its spectrums against a library of reference spectra, a process known as spectral searching. So mo ni siya ang equations pod pag-identify sa compound sa unknown compounds where the D is a cumulative differences, A sample is the sample absorbance at wavelength, A reference absorbance reference compound at the same wavelength, N is the number of digitized points in spectra. So mao na siya ang qualitative analysis sa or qualitative application sa UV spectroscopy. So, UV spectroscopy is used to check the purity. So, one example of the UV is used to check the purity of the olive oil. So, it's impossible to differentiate the saturated and the unsaturated fatty acid present in olive oil. So, mao na siya ang one example sa qualitative application sa UV spectroscopy. So, that's all.
Used for analysis of trace analytes in macro and meso samples. So this method is particularly versatile, no? So by adjusting the concentration of the sample, it has a different levels of analytes that can be detected with precision. So for the major and minor analytes, the sample is typically diluted prior to analysis. So this dilution helps in achieving the accurate measurement, so without the interference and from higher concentration elements. So in contrast, when it comes to ultra-trace analytes, kay mag-present siya og extremely nga low concentrations with the process nga mag-involve sa concentrating sa sample. So this concentration it is the step that increases the detectability sa ultra-trace components. Allow po siya nga mo precise identification and quantification. So, through strategic sample preparation, so this analytical approach can cater to a wide range of analyte concentration, from major and minor to ultra-trace levels. So, it making it a powerful tool, no, in chemical analysis. So in accuracy, it is under normal conditions, and it achieves a relative error of 1 to 5% with UVs. It is absorption in spectroscopy, which is straightforward. So in this level of precision, it is typically sufficient for many analytical purposes. So it provides a reliable data on concentration of analytes in the sample. So, however, the accuracy of this measurement is often constrained by the quality of the blank used in analysis. So the blank serve as a reference point para ma-account niya ang mga background absorption and instrument noise. So, any impurities or inconsistencies in the blank can introduce errors. So, thereby, mo-affect siya sa accuracy sa measurements. Then, it ensures the blank kanang high quality and properly prepared dapat. Kasi, it is crucial for minimizing errors. and mo-obtain po siya og accurate results. So, ang UVs kay mo na siyang absorption sa spectroscopy can para ma-deliver niya ang low relative errors under normal conditions. So, overall, ang accuracy is mo na siyang significant niya nga mo when it comes to integrity kay nana siya blank solution with the use of this process. It says here in absorption spectroscopy, ang precision is limited in intermediate errors. So, primarily due to instrumental noise, mo na siyang mag-introduce sa measurement sa absorbance. So, mo ni siyang errors nga kanang mo significant nga impact or important impact makita ang results. So, particularly kay ang mga ranges of absorbance. So, in precision, generally, it has a extremes of absorbance measurements. For low absorbance, where are the incident light intensity or ang PO, mo na siyang approximately equal to transmitted light intensity or ang PT. So, mo na siya ang signal to noise ratio decreases. So, mulo, no? So, making it difficult to distinguish the absorbance signal from the background noise. So, mas similar siya sa high absorbance. Kay ang high absorbance is mo na siya mo transmit light intensity or ang PT mo approach siya sa zero. So, it reduced amount of light passing through the sample also leads to increased noise and mo decrease iyang precision. So, always remember, in precision, it leads to increased noise while iyang precision is mo decrease. So, as a result, mo na siya dili siya constant, but varies with transmittance. So, in the mid-range of absorbance, whereas iyang extreme conditions kay mo dominate. So, ang precision kay mo tends to be better, but understanding this relationship is crucial kay mo optimize manggod iyang measurements and mo improve po iyang reliability para ma-obtain nila ang absorption spectroscopy. Sensitivity kay mo na siyang molecular absorption method nga mo defined by the slope of a Beer's law calibration curve. So this sensitivity is mo determine siya sa two key factors, which is mo na siyang analyte absorptivity and the path length of the sample cell. So, in absorptivity, kay mo na siya often ma-denote as epsilon. So, mo ni siya ang measure of how strong the analyte absorbs light at a particular wavelength. So, mapod na siya intrinsic property sa analyte nga mo-vary siya sa wavelength, sa light nga magamit or ma-use. So, in path length, kay mo na siyang nag-represent sa B, which is the B is the distance that light travels through the sample. So, typically, the length of the sample cell. Mo na siya sa the path length of the sample cell. Beer's law, A equals to epsilon BC, where A is absorbance, epsilon is mo na siyang molar absorptivity, and B is for path length, and C is the concentration of the analyte. Then, ang slope niya is calibration curve, whereas A versus C. Then, ang epsilon and B is mo na siya ga-illustrate sa both absorptivity sa analyte and the path length sa sample cell. So, by increasing either the absorptivity or mo na siyang mag-choose sa optimal wavelength sa analysis, then, ang path length pod is mo na siyang mag-use sila og longer sample cell. Ang sensitivity manggod is ang sensitivity sa molecular absorption method kay mo enhance. So, mo allow nila ang mas precise and accurate when it comes to the process of analysis. So, when it comes to selectivity, it says here in molecular spectrophotometry, okay, ang interference is rarely a problem. And this is large due to the ability to select specific wavelengths for analysis. So in many cases, it is possible to find wavelength at which only the analyte of interest absorbs light. And it also minimizing or eliminating the potential for interference from other substances. So this is a unique absorption characteristic because it has a different molecules nga mo allow sa selective wavelength choice. So by carefully choosing a wavelength, whereas the analyte is a strong absorption peak, and yung other potential is mo interfering species do not. So it is accurate and specific measurements can be obtained. So this selective absorption kay mo ensure siya sa recorded absorbance nga mo primarily due to the analyte lead sila sa more reliable and precise analytical results. So, sa time, cost, and equipment is, mo na siya ang analysis of sample by molecular absorption spectroscopy para maalaw nila ang quick quantification of analytes. However, has a additional time may be necessary no para sa analyte itself nga dili inherently mo absorb sa light at a chosen wavelength. So, in such cases, manggod, the non-absorbing analyte kay mo converted into absorbing form. So, this conversion process can be involve chemical reactions nga mo produce sa compound para mo exhibit a suitable absorption spectrum. So, this step kay ma-add sila sa overall analysis time. Mo ensure po sila nga ang ilang non-observing analytes kay mo accurate measured during molecular absorption spectroscopy. So, despite the need for potential preparatory steps kay ang kaninga method kay mo remains sila nga efficient and effective for a wide range of analytical application.
So, good day again. Now let's move on to our next topic, which is the molecular spectroscopy. Let's start with the emission spectroscopy. So, an analyte's excited state possesses an energy, it is denoted by E2, and an analyte's lower energy state is denoted by E1. So, if an analyte returns to its lower energy state, like for example, ma-reach na niya ang excited state and then mobalik siya sa iya ang lower energy state, is ang tawag nato na ana nga process is relaxation. So if there's an relaxation, so naay excess energy na makuha. So excess energy is denoted by delta E. So as you can see in our presentation, there is an equation. So delta E is equals to E2 minus E1. And the difference between these two is our excess energy. Okay? So, excess energy is denoted by delta E. So, if there's a excited state, so therefore, there is an excited state's lifetime. So, typically short lang yun ang lifetime sa excited state. So, the amount of time an analyte, which is denoted by A, spends in its excited state for only 10 to the power of negative 5 to 10 to the power of negative 9 seconds. For an electronic excited state lang na siya. But, in the vibrational excited state, its lifetime is 10 to the power of negative 15 seconds only. Okay? So, in the relaxation process, the analyte's excited state occurs through several mechanisms. By the way, ang analyte's excited state is denoted by A, ang naa siya'y asterisk sa taas. So, there are three mechanisms as what I have mentioned. So, first is the collision with species. Second is the photochemical reaction. And third is the emission of photon. So first, ang collision with other species is ang excess energy niya is released as heat. So as you can see diri sa taas, ang atong analyte's excited state is ang iyang pag-release is through heat. release as heat. And then sa photochemical reaction pod is nag-involve siya og simple decomposition. As you can see sa tuwang presentation, na simple decomposition nga makita. And then naapoy reaction between analyte's excited state and another species. So in both cases, the excess energy is used up in the chemical reaction or released as heat. So in the third mechanism, the excess energy is released as a photon of electromagnetic radiation. As you can see in our presentation, ang analyte's excited state is released as a photon of electromagnetic radiation. Now, the release of a photon following thermal excitation is called emission. Ang release na siya sa photon ha. And then, that following the absorption of a photon is called photoluminescence. Now, unsa ning photoluminescence? So, let's move on to the photoluminescence spectroscopy. So, in the photoluminescence, there are two categories: fluorescence and phosphorescence. Fluorescence is the emission of a photon from a singlet excited state to the singlet ground state. Emission, so ang pagbalik niya. And then sa phosphorescence pod is the emission between a triplet excited state and a singlet ground state, or between any two energy levels that differ in their respective spin states. So now let's have a drawing. Sa mahitabuan niya. Now, sa ground state, a pair of electron in the same electronic ground state have opposite spin. So, naa siya sa same nga ground state but opposite yung spin. So, for example, munit ang ato ang ground state. We have a two ground state. We have a two state. So, ang sa singlet ground state is na sila sa same nga state daw but different. Nasa same nga ground state but different og spin. So mo ni siya ang nangu. Different og spin but same sila og dikitan. Same sila og gitugpahan. Na sila sa ground state. Mo na siya ang singlet ground state. So in the fluorescence pod, it is the emission. So ang pagbalik sa photon from a singlet excited state to the singlet ground state. So, mo ni siya ang namong. If an analyte, sa fluorescence niya, if an analyte absorbs an ultraviolet, one of its valence electrons moves or jumps from singlet ground state to an excited state. But, same ra gyapon og electron spin nga pareha sa singlet nga ground state katong ganiha. So, sa fluorescence is once na maka-absorb ang analyte of ultraviolet, mo jump daw ang iyang electron from singlet excited ground state to singlet excited state with the same spin as the singlet ground state. So, mo ni siya iyang naong sa fluorescence. So, the emission of the photon from singlet excited state to singlet ground state is called fluorescence. The average lifetime of an electron is in the excited state is only 10 to the power of 5 to the power of negative 5 to 10 to the power of negative 8 seconds. So in some cases pod, sa phosphorescence, ang atong phosphorescence is the emission between a triplet excited state and a singlet ground state. So, mo ni siya. So, phosphorescence, diri nga, an electron, a single excited state, is transformed to a triplet excited state. But in this scenario, in the spin is no longer paired with the ground state, which means wala na'y araw nga paubos. Same na siya og spin but different og state. Mo ni siya ang phosphorescence. Okay? So, emission between triplet and singlet ground state or any two energy levels that differ in the respective spins is called phosphorescence. And the average lifetime of phosphorescence is 10 to the power of negative 4 to 10 to the power of positive 4 seconds. So, fluorescence for qualitative and semi-quantitative analysis dates early to mid 1800s with more quantitative methods in 1920s. So though mas nauna na discover ang phosphorescence, but wala kayo natagaan og atensyon ang phosphorescence not until sa pagdiscover sa fluorescence. Sa pagdiscover sa fluorescence ay haradayon natagaan og atensyon ang phosphorescence. Okay? So now, let's move on to the fluorescence and phosphorescence spectrum or spectra. As you can see sa to ang picture diri, na ay color. Ang kaning black nga line nga nasa ubos is mo na siya nga to ang ground state. Samantala, ang kaning nasa taas nga green is ato ang excited state. Ang kaning S1 og S2 ug S1 is pareha silang mga single state. While diri, makita na to nga na blue nga arrow is mo na siyang absorption. Ang kaning pa-down na arrow nga color red is fluorescence, while ang diri sa kilid is phosphorescence nga color orange nga arrow, orange or yellow. Now, pag sa fluorescence, pag ang analyte is maka-absorb og ultraviolet, na excitation mahitabo. Ma-absorb niya, so na excitation mahitabo. And then pag abot niya sa excited state, na vibration. So na ay lifetime niya dito og kanus ara siya taman sa excited state. So pag abot niya sa excited state, na internal conversion wherein ang emission na din na siya, ang relaxation na din na siya. So once mo relax na siya, mubalik na din na siya sa ang lower energy state. While sa phosphorescence pod, same ra ni silang S1 ug S2 ha. Ang phosphorescence darita. So ang phosphorescence is same ra gyapon siya og pamaagi na absorption, na excitation, na vibration and all. So good ta. So diri na absorption. Maka-absorb siya na absorption, na excitation, na lifetime diri nga mahitabo. And then kung sa fluorescence na internal conversion, sa pag-abot sa phosphorescence, muambak siya from single state to triplet excited state. So na ay intersystem crossing, kaning naa diri intersystem crossing, kay maambak siya. So na ay lifetime. And then same sa fluorescence, na nadayoy pag maabot na ang lifetime, pag ma-reach na niya ang iyang kadugayon sa excited state, mo relax na din na siya. Emission na din ang mahitabo, mo relax, and then mobalik na siya sa lower energy state. So mo to siya ang mahitabo sa fluorescence and sa phosphorescence. As you can see sa tong spectrum, ato na siyang foresee o ma-imagine o unsa gyoy diagram ana niya. So that ends my discussion. Let us all listen to our next presenter as the continuation of the topic.
Hello everyone, I am Aikim Pakolba, and now let's proceed and tackle about radiation-less deactivation. It's the process where a molecule relaxes without emitting a photon. So for example, vibrational relaxation, in which a molecule in an excited vibrational energy level loses energy by moving to a lower vibrational energy level in the same electronic state. When we say electronic state, it is the specific arrangement of electrons within an atom for a molecule. Now, for example, think of a swinging pendulum. If you can circle our activity sa astronomy, which is demonstrated by one of our classmates using the swinging pendulum. Now, when you push the pendulum to swing higher, it eventually slows down and comes to rest at a lower position. Now, same way sa molecules, when it is at the lower vibrational state, after being excited, it loses energy. And the process of calming and loses energy of electron is what we call the vibrational relaxation. Another form of radiationless deactivation are first, the internal conversion, in which a molecule in the ground vibrational level of an excited state passes directly into a higher vibrational energy level of a lower energy electronic state of the same spin state. Now, for example, naihagdanan. Now, think of a molecule as an object that can move at different between different energy levels. So if naay hagdanan, then ang molecule is naa sa higher position sa hagdanan, then mo dito siya sa lower position without going through all the steps is what we call the internal conversion. It's like taking up the shortcut between different energy levels within a molecule. Okay, now let's proceed to the another form is the external conversion in which excess energy is transferred to the solvent or to another component of the sample's matrix. For example, na kay hot coffee. Then when you place the hot coffee on the table, the excess energy will transfer to the table, which making the table warm. So, mo na siya atong gitawag external conversion. The process of the excess energy is transferred to the surrounding environment. Okay, next is the intersystem crossing, in which a molecule in the ground vibrational energy level of an excited electronic state passes into one of the higher vibrational energy levels of a lower energy electronic state with a different spin state. Now, kung nakit playground, dan sa playground naman ay swing kanang yan. Then sa duyan, ang nagsakyan na consider it as molecules. If kanang isa ka molecule, iswing nito na higher, and ang isa is has different spin state. Okay, by the way, ang spin state is actually two possible orientations, the spin up and the spin down. So if kanang duha ka swing is na a different spin state, it's like intersystem crossing. Una siya itong gitawag intersystem crossing. Okay? Good. Okay, next is the relaxation by fluorescence. Fluorescence occurs when a molecule in an excited state lowest vibrational energy level returns to a lower energy electronic state by emitting a photon. Ang example ani guys is kanang bitaw glowing stick kanang glow in the dark it depend like ka siya. So muna siyang example. As it releases light, no magkinihinan siya papalo. So muna siya ang process na gitawag na relaxation by fluorescence. The process of releasing light and the process of calming and emitting the light is what we call relaxation by fluorescence. So other topics will be discussed by my colleagues.
The relaxations of phosphorescence. A molecule in a triplet electronic excited state, the lowest vibrational energy level, normally relaxes to the ground state by an intersystem crossing to a singlet state or by an external conversion. Phosphorescence happens when the molecules relaxes by emitting a photon. The phosphorescence happens over a range of wavelengths, all of which are at lower energies than the molecule's absorption band. Here's the equations, which similar to fluorescence, however, the IP were the intensity of phosphorescence, and this figure is the phosphorescence quantum yield. Here's the true figure most favorable sa molecules with transitions. Ang average lifetime sa phosphorescence can be quite long, ranging from this 10 to the power of negative 4 minus 10 to the power of 4 seconds. The phosphorescence quantum yield is usually quite small. An improvement sa kaning figure is realized by decreasing the efficiency of external conversions. This is accomplished in several ways, including lowering the temperature, gamit a more viscous solvent, depositing the sample on a solid substrate, or trapping the molecules in solutions. Now, the excitation versus the emission spectra. Photoluminescent spectra are recorded by measuring the intensity of emitted radiations. Emitted radiations as a function of either the excitation's wavelengths or the emission wavelengths. Here the definition between the two spectra. The excitation spectrum is obtained by monitoring emissions at a fixed wavelength while varying the excitation wavelengths. The emission spectrum is a fixed wavelength is used to excite the sample, and the intensity of emitted radiations is monitored as functions of wavelengths. The two emission spectra is one sa fluorescence ang isa sa phosphorescence. Here's the example of phosphorescence. In A, mani siya ang nawang sa natural lights, and the B is, ang kaning letter B is a long wave using the UV lamp, and lastly, in total darkness.